Yeah, please go ahead.
Okay, as we said, we have this residential building. It's already modeled in ETABS. The green, I will show you in 3D. The green part is the column, the yellow part is the beams, and the gray part is the slabs. And this one is finished modeling. Actually, modeling, it's need special requirements, so I will not go for it. I will go to how to compute the period and how to apply the seismic force on ETABS. Okay, now we need the period from the model analysis. Actually, there is two ways to know the period of model analysis. First, I will show the simplest way. First, we should analyze. We will analyze the structure. Okay. Now, this is the deformed shape for dead load. Like it's shown this one for dead load. We should see the deformed shape from here for the mood. Actually, every mood have its own period, and there is some models that go for X direction, and one go for Y direction, and one go for rotational direction. So the input period that we should insert, we should put the first X direction period. For this example, we will see what is the first mood. As we can see, the first mood is going to X direction. I will start as an animation. Okay, as we saw, the structure is going for X direction. And actually, this is the TX. And it's not the case for all the structure. This is characteristic depending on the structure. Some structure maybe go for Y direction for the first mode. Some structure maybe rotate, and it's depend on the structure itself. So we see it's go for X direction, and the period is giving here is 0.713 seconds. So this is the TX actually that we will compare with. Let's see the second mode. Okay, we saw that the second mode was going for Y direction. So this is TY, and this is 0.67. And let's see the third one. Okay, the third one is rotational. Actually, maybe in some cases we will have rotational as a first mode, but it's not a favorable case. So the favorable case as this case, having the transition period for X and Y first, or Y and X, it doesn't matter. But if we have rotational at first, it's not favorable. So this is the first method to see the period. But sometimes it's not a clear way. Sometimes we have some rotation with the X period or with the Y period. So we will go to another way to know how we can determine the X period and Y period. So we will go for display, show table, and structure output, model information for the model participating mass ratio. Okay, sorry. So we have this table. Okay, to better clarify the table. Okay, we have the UX, the displacement in the X direction, and in the Y, and this is the rotation. So as we can see, the model one have the period of 0.714 seconds. And sorry, this is the mass participation ratio. It's not the deformation or the displacement. So the mass participation ratio in the X direction is taking as 0.88, and in the Y0 and the Z0, this is navigate us that this mode is for the X direction. If we go for the second mode, we see the period is 0.672 seconds, and the participating ratio is 0.87 in the Y direction. So this is obviously it's a Y direction. This is TY, and this is RZ, mean the rotation. So this is referred that the third one is for rotation. As we can see that the first mode also is X direction, and fifth mode, but this is the most important period for the first three period actually. So we have TX and TY. Let's go back to slides to compare.
Amr, just wait a moment, please. Go back to that. Yeah. Okay, here, maybe I need actually now to a little bit explain about this. Okay, so actually your explanation was nice. Okay, so just I want to put, some other points as well. So here, actually, we have the pure translation movement under, different, let's say, modes. Okay, as you can see here. So we have actually here by default, we have 12 modes. Okay, so here it is 12 modes. So in ETABS, by default, actually is 12. You can, let's say, modify, this number of modes. It depends on the, let's say, the mass participation factor. So in ASCE, or let's say, in almost every code, so you need to actually calculate the, let's say, the percentage of the participation mass in the seismic action. For example, here you have the 0.88, so which means 88% of the mass is participating in mode number one. So if you remember from the dynamic class, assume that here actually you have the single degree of freedom system, or maybe this let's say multi-degree of freedom system. Okay, and then so you're applying the lateral force, okay, to this structure or system. So once you have this, so here you have 12 modes, but assume that, for example, you have let's say 3 or 4 modes. Okay, so the mode one, or let's say the maximum participation factor. So in the mode one, so here I will say mode one. Let's say mode two. And then here you have the mode number 3. Okay, and maybe the last one, which is mode number 4, is here. Okay, so in mode number 1, so you have the displacement exactly here in X direction. Okay, and then here actually it is 88% of the mass participating in the this direction. Maybe in mode 2, so here look at the let's talk about, this is actually now the X. Okay, so in mode 2, assume that this is mode 2. Okay, so because here for mode 2 and 3, so we have 0, and here we just simplify to 4 modes. Okay, 1, 2, 3, 4. Okay, let's talk about this. Assume that they are the effective modes. Okay, in the mode 2, so you have 8% only, almost 8%. So which means here you have something like this. Maybe here this is 8%. Okay, and then so here you have 2% only. Okay, so here you have 2%. Okay, and finally you have less than 1%. Okay, is about 0.6. Yeah, is only, which is almost actually nothing in the last mode. Okay, 0.6. Okay, so in this manner, so we understand that the governing mode is mode number 1. Okay, so assume that, for example, you have something like this. So let's say the mode number 1, for example, the for example, the rotation is like this. or maybe I can make it more clear. For example, in mode number 1, maybe you have actually something like this. Okay, in mode number 2, maybe you have something like this. Okay, and then in mode number 3, maybe you have some, let's say, deformation, maybe like this, let's say. Okay, but the overall deformation of the structures follow this mode. Why? Because here 88% of the mass actually participating in mode number 1, and this is actually the deflection. Definitely here the deflection is let's say, I will say that the deflection 1 is definitely more than deflection 2, and also deflection number 2. Let's say here it is more than, usually is like that. Okay, and then deflection in mode 2 also is bigger than deflection number 3. Okay, but in some rare conditions, not always the mode number 1 is the governing mode. Okay, sometimes, for example, in mode number 1, maybe you have the torsional mode. So which means, something happened here in our case in mode number 3. So maybe here depends on the configuration of the structure that you have. For example, maybe you have actually something like this. Here you have the shear wall. Okay, maybe here you have another, let's say, core wall, something like this. And then definitely, the center of the rigidity, will move somewhere. For example, here, assume that the center of mass is somewhere here. Sorry, the center of the pillar, okay, is here. And then so just by adding actually this wall and this wall here, so you are moving the center of the mass to somewhere here. Okay, and this actually affect the let's say the mass participation factor under different modes. Okay, in this case usually you won't get the pure translational mode in X direction or Y direction. Usually in these cases you have the torsional mode in the first mode. Okay, so you need actually to understand this, and also this gives you this brilliant information about the let's say the torsional behavior of your structure as well. So once in the, usually in the first mode, once you have the torsional mode, so it means that actually you need to consider or reconsider actually the configuration of your structure. Okay, so this is the first thing. The second thing, so which is I think it is out of our class right now. So you can increase the actually the eccentricity. Usually actually is 5%. It is limited by 5% from the code. But if you want to keep this one, or let's say this configuration, so you can increase the eccentricity maybe to more than 5%. But definitely you will come up with a very conservative design. Okay, so you need to let's say increase the size of the structure maybe in different parts. Okay, so this is the thing, and this information can be obtained from model analysis. Yes, Ambra, maybe you can continue. By the way, from here also you can use the table as well. Okay, so if you are not familiar with ETABS, so also you can use the table from here as well. But all the ETABS users, just like me also, so always we like to go to the tables. Okay, so yeah.
Yeah, true.
Yeah.
Okay, so we have the first TX and as 0.714 second and TY 0.672 second. We should compare it with the.
By the way, Amr, sorry, I'm interrupting you a lot. Can you just calculate how much is the mass participation factor?
Yes, so it's already calculated.
Yeah, is here. Okay, so it is 19.9. Okay, so which is correct. So always you need to check this value. Okay, if it is less than 90, so yeah, you have two options. Okay, even here I believe that you will use the eigenvectors. Yeah, so you can use you can use the Ritz vector. Okay, to just get the effective mode. Okay, so this is actually which means we call it actually missing mass. So you don't have any missing mass. Okay, once you are using the Ritz vector. Or another solution is that you need to increase the number of modes, okay, to catch more masses during the model analysis. So this is the way. But always you need to check this mass participation factor should not be less than 90%. Thank you, Am. So I will. I don't interrupt you anymore. So please go ahead.
No problem. Okay. So we have this Tx and Ty. We know how to know which Tx and which Ty. And like the doctor said, it's a rare case to have this in real life pure, but you will be able to differentiate because the higher value will be in Y or X or RZ. So you can differentiate what is the period for which direction. So in our case, it's 0.714 and 0.672. So let's compare it with the one that we calculate. This is Tx that from the model, and this is Tax multiplied with Cu, it's 0.824. So we should take the minimum between these two. The minimum is 0.714 seconds. So we use in the X direction 0. Actually, this is automatically doing by ETABS, but the older version of ETABS sometimes have error in this step. So you should always know this actually before using ETABS also. Also for the Y direction, we have 0.672 and 0.824. The minimum is the one that from the model. Okay, let's see how we can apply the load on the ETABS, the seismic load. Let's unlock the model. Okay. First, ETABS is a user-friendly. Like if you go for your project, first you will see the define window. The define window will have the material, the section, the diaphragm, the load cases, the load combination. Everything that you need define will be in the first window as defined. Then you need to draw the elements. Like every tool for drawing the element also exists in the draw window. Then the assigning, if you want assign load, if you want to do some assigning also. So it's familiar, like it's friendly for users actually. This is why it's commonly used ETABS between engineers. So first we want to define. We want to define the seismic load. We go for load pattern. Okay, now we will say, we said that we should have for the two individual direction. This first one we will see EQX, and the type is seismic. We can see which we can define every type of load, seismic, wind, pre-stressed, everything. So we will go for seismic. Actually, seismic drift is more related to calculate for the drift calculation. So we'll go for normal seismic. The ETABS 21 have ASCE 722, but as the doctor said, I used ASCE 716. So I will go for ASCE 716. And then we will go for EQY. Okay. Also ASCE. Okay, let's see what we can define. The first one is the direction of the loading and the eccentricity that the doctor talked about. This is the 5%. This is the critical one. It should be included. And this is the direction. I will not consider this because also this related to torsional irregularity. If we talk about torsional irregularity, I will go to this, but now I will not consider any eccentricity. We'll go to the X direction. It will apply on the center of rigidity. So this is the time period calculation. We see CT and X before, and I told you this is compute. I will go to here. Okay. This is CT and X. So we have CT and X. We have concrete moment resisting frame. So we will use this value 0.016 and 0.9. So this is 0.16 and 0.9. Actually, you can, because we obtain it, we can go for user define automatically. And usually as old user, I use the user define because sometimes I told you it gives some errors, but now in this one I didn't saw any error until now, so we will go for this. And this is the distribution of shear force. It's from the base for the last story 5. And here we should insert the SS and the S1 and the T large and the site class. So let's go back, see what SS and S1. Okay, SS is 0.51 and S1 is 0.18. Okay, T large is 24, but it's not that important. So the site class, as we said before, it's C. So we see it's calculated by itself automatically, the FA and FV. It can be calculated by the program, and it calculates SDS and SD1 by the program also. So this is the SD1 and SDS by the program. Let's compare it with the one that we compute. This is the SD1 is 0.18. This is 0.18. And the SDS is 0.44. It's also 0.44. So I told you before, this is for the ASCII 716, the program automatically calculate this. For the ASCII 722, you should provide SDS and SD1. So this is the response modification factor and the overstrings and the deflection and the importance factor. We obtained this from the previous tables. From this, it's 835.5. And it's actually same here. There is no need to change 835.5, and the occupancy importance, its importance factor, this is 1. So this is for the X direction. We should redo it for the Y direction. Okay, 016, story 5, I think 051, 018. See why this is. Okay, and this is same. So now we define the load. Let's analyze and see how ETABS will calculate it and how we can know what forces it's applied and how we can see everything. Also, there is 2 methods to see the shear force and the Q that produced by the equivalent lateral force. I will go for the first method, but I prefer also the second method from display story response plot. Okay, we will go for autolateral load to story, and this is EQX. It shows how it's provide the forces over the structural height, and this is the Q. This is not the V, the cumulative shear force. This is for X direction, and we can see it's approximately 75 kilonewton for the 5th story, and this is for the EQY. We can see there is a little different in the shear force between X and Y. We will see why. So if we want to see the story shear, we go to story shear and then EQX. This is the cumulative one, the story shear. It's around 215 kilonewton for the X direction, and it's more in the Y direction. Okay, this is the first method. The second method that I prefer, because we can see how ETABS compute everything, I will go for File, Create Report, Add a User Report. Okay, I will select EQX and EQY, and here EQX and EQY. I will deselect everything because this usually we use it for obtain the final report, and I will only press on auto seismic load and auto seismic calculation. And I will create the report. Okay. Is it clear?
Yes, Amr, yes.
Yes.
Okay. Okay. This is the auto seismic load. This is show how what values that the software used to calculate the shear forces. For the EQX, the period that he used 0.714. Okay, this is, as we can see, this is the same that we select before. And for the EQY also 0.672. So in two cases, he made it right. Like he chose the properly period. And this is the seismic coefficient, what the final value, and this is the weight. I actually, in this example, I took 25% of the live load, so we will verify it later. And this is the base shear for X and Y. We see this X have different one than Y. And this is related to eccentricity, but we didn't took the eccentricity. And this is the SS and S1 that we put, and this is the site class FA, FD, SDS, everything, and R omega CD. Actually, it's good to see these tables after we finish assigning seismic load. And this is the values. We see that we provided at feet, but even if we use meters, ETABS until now, he put this on feet, but he gives a right value actually. So this is S1 SS as a given. He compute FA, FV, he calculate SMS, SM1, SD1, SDS. And this is the seismic response coefficient relationship that he used. This is the CS, and this is the CS maximum, and this is the CS minimum. Okay. But actually, he didn't mention which one he take. Like, if I see, I don't know if he used CS or CS max or CS minimum. This is not right, actually, because in this case, he used CS max. So we will see also how it's used. So this is the shear force, 217 kilonewton. And this is the distribution of the shear force over the story. You see here, it's give you right values. So I think it's better to see it in this way. And it's again for the Y direction. So let's try to verify these values with the manual calculation. Okay. As we see, we have first to see if he compute the seismic weight, is it true or not? So we compute the area of the slab, it's 240 meters. We assign, actually, we assign 5 kilonewton dead load, and this is 5-story. And we have 3 kilonewton per meter square live load, and we take 25% of it, and we multiply it with the area on 5 stories. So the seismic weight, this is a screenshot from the ETABS. It's true, 6,900 kilonewton. So we will go for the X direction, actually, we'll just verify. So the CSX is SDS R over II. It's 0.44 over 8 over 1. It's 0.055. We see it's different than here, but we will see why. We said in most cases, our T will be less than T large, so we will use this equation. We'll not go for the second equation. This is the CS max. The difference between this and this, we use here SD1, not SDS, and we use the period T that we select from before. So here we have 0.18 over 0.714 multiply 8 over 1. We see here that the CS max is less than the CS that computed, so we should go for CS max, 0.0315. And this is the one calculated by, chosen by software. So he chooses right the max value. And this is the minimum, of course, it will be less the minimum value. So it was selected right for the CS max, and he gives 0.315, and it's less CS. So we calculated, we multiply CSX, multiply with the seismic weight, we have 217 kilonewton. So the values is right. And if you want to see why X is different than the Y, we see here, this is for, okay, this is for the X direction 217, and for the Y direction 231. Why? Because we see that he go for the CS maximum, and CS maximum has the period, and the period for the TY is less than the period that for TX. So we will have more, here we have 0.672, so we will have more shear force. So this is why we have different value for the X direction and Y direction. And I can show you another model actually that have different, this model have different story height and have different spans. So we just took one spans out, and the spans here is 5 meters. So what you think that will change? Anyone have any idea? For the period, let's say.
Yeah, maybe our friends can participate. Any idea, Mr. Iqbal? Take. Kawan?
Like the period will
be changed.
Increase,
the
decrease.
Because
yeah,
the period is related to the rigidity and aim, yeah?
Yeah. So in this case, it will increase or decrease. We took one spans out.
I think it's increased.
Yeah, true. It will increase. As we can see, the mood also in the X direction, but here it's 1.35 seconds. So here we have a higher mood, because here the rigidity of the structure is less. So we'll have higher deflection and then higher period. And we can see that also for the Y, it's 1.34. So in this case, we should see that the one that we calculated manually should be less than the one that computed by the model. And let's see, actually we insert approximately the same values, but let's see what if he do it right. Like if we go for define load pattern, okay, here I have defined too many things. If we see, we have the period here, and we will see if he did it right or not also. Okay, I will go for file create report. I will go for EQX. Okay, as we see, the T that he used is less than the T that given by model, and it's 0.869. So just to check it last time, I will go to Excel sheet, not this one. Okay, this one. So here we recalculate the whole thing, the HN and the CU, and like the period that giving the TA and CU TA, it's 0.869. So he did the comparison in right way, and I don't know if you can safely do this also always, but I prefer to always check what period that the software use. And
Yeah,
that's it.
definitely we need to check the values obtained from the software, with our hand calculation. Okay, so at least, maybe for one time or, 2 times, you need to do that. Actually, you need to understand about the accuracy of the software calculation and result. Okay, so we should not blindly use the software. So this is the thing. Okay, so that's why it is strongly recommended, as I told you, at least, before using the software, try the software, test the software, by, just comparing the result between your hand calculation and the result obtained from the software. Okay, maybe for one time, second time. Okay, so if you found everything is fine, so then you can go ahead. And another thing that actually, I want to put it here is about the version of the software that you are using. Okay, so maybe here actually, you are using the, let's say, the student license, or I don't know, maybe, the correct version of the software. And so you need to pay more attention to the result. Okay, but definitely if you are using the, let's say, the verified license from the CSI product or CSI company, so definitely, the result actually, can be trusted, because, simply I can give you this example. As we know, in 2008, Burj Dubai or Burj Khalifa, was designed by ETABS. Okay, so which means, ETABS already has its test. Okay, so from, since 2008. Okay, and definitely, the engineers or the companies actually, they didn't use ETABS blindly. So definitely they compared the ETABS result with the, I don't know, maybe, hand calculation or other solutions. Okay, and finally, they understood that ETABS calculating the, let's say, forces, the designs, let's say, the seismic, let's say, parameters very nicely. Okay, and at that time, actually, it was ETABS, if I'm not mistaken, ETABS 9. Okay, so they used it actually, for design Burj Khalifa. Nowadays, we are actually using ETABS 21. So just you can imagine, how much improvement they put in the software, and definitely, they just debug the bugs. Okay, so once you are using, some proven software like ETABS, okay, so you can actually, rely on the result, but still, for first time or second time, just check the result for yourself, because our responsibility is really heavy. Okay, and we are designing the structures to just, for people, to live under the structure. Okay, under the sailing of that structure, and God forbid, and if any bad scenario happen, especially, during the earthquake. So we have recently, a very, very bad experience in Turkey. Okay, and definitely, I believe that maybe at least I can say that 50% of the structure was designed by ETABS. However, in Turkey also they have their own solutions as well. Okay, they have it Prota structures. Okay, but definitely it wasn't the fault of ETABS or Prota. So because it is actually, our responsibility, to understand the problem, and also to apply the, let's say, knowledge in a correct way to the software. So this is the thing that we need to understand. Otherwise, we can say that, yeah, so the result from the most of the software that we have available in the market actually, are correct. Okay, but at least we need to understand what we are doing. Okay, so this is the most important thing as an engineer. So we need to think about it. And since we are actually, in the postgraduate level, so definitely we need to guide, let's say, the junior engineers, or let's say, the degree engineers, to understand about this, because we have actually, a wide experience about the junior engineers, or let's say, degree engineers, that they don't understand the seismic design of a structure very well. Okay, so that's why at least I could see that many of the models that I'm receiving, from different companies, seismically, they are not correct. Okay, so in putting the information and data, so it doesn't matter. So some of them using ETABS, Staad.pro, Prota structures, or maybe, SIPE and other solutions. So we need actually, to understand what we are doing. And as our friend Amr said. So at least, you know, for first time or second time, just check the result with your hand calculation. And once you are satisfied with this, so go ahead. Okay, Amr, yeah, maybe you can continue.
I finished it already.
Okay, so guys, okay, let me